The idea is to, we will start with the lowest local lemma, but we will study a special case when all the special case of CNF and with some special requirements. So we will not prove the original version with this strange pi times 1 minus pj. So this we will not achieve. But still it will be more non-trivial case than the compared to what was in the lecture before. Then we just prove that we can color the graph in with degree d in d+1 colors, which was completely trivial. Here we still have a non-trivial statement which cannot be not clear how to prove without the lemma. So let me formulate this special case. So imagine we have a CNF when every KCNF, so every clause has k variables. So every clause prohibits some combination of k values. And we want to show that there exists a satisfying assignment. But of course, we need some condition. And condition is that each clause has at most c to the, I think, k minus 3, maybe there will be some other constant, we will see, neighbors. And neighbors are clauses that share a variable. So this is the standard, just existential statement, what exists. And there is an algorithmic version which gives specific algorithm that finds some satisfying assignment, a satisfying assignment. And let's write it in top-down version. The main algorithm is for every clause fix this clause. And fix this clause will be some procedure. And you can guess what are the post and preconditions for this procedure if you want to fix some clause C. You can imagine what should be before and what should be after. And before, it's reasonable to assume that C is false. And after this clause, it's reasonable to require that C is true. And there is an exercise for programming course. Is it okay? So imagine we have the procedure which has satisfied this pre and post conditions. And then we fix every clause. Is it enough to make a satisfying assignment? And if not, what else we need? What should we write in the post condition?
All the clauses which were true.
Yeah, of course, it's stupid if we can fix just clauses. It's trivial. The problem is that this clause should be true, and all clauses which were true are still true. So after this, I guess that you have no doubts about the correctness of this algorithm. Okay. Then let's try to write the procedure fix a close. The C is false. And what we do is what was explained before. So we resample our close C. So we choose new fresh values of variables for our close. And then, of course, there are two problems. First, maybe didn't fix the close. If we are especially unlucky, we can make the same wrong assignment as before. And so there is some small chance that we are still in the bad shape with this close. But also, the more important problem, which is more difficult, is that while resampling this close, we can destroy other clauses which were previously were true. So we, for all neighbors C prime, including C itself, if C prime is false, fix C prime. Yeah, actually, now I see that this is, I was wrong when saying that our main algorithm was correct. There is some error. Probably you can now, knowing that the error is there, you can say what is the error. What should we do? It's not a good idea for every clause fix it. What we should do, we should say that if C is false, because our procedure doesn't specify our requirement for the procedure doesn't specify what it should do if the C is true. Maybe if it's true, it should destroy it or destroy everything or whatever. So we need here we need also this check. So if C prime is false, then we fix C prime. And then it's if we look at this procedure, the good news, it's obviously correct. Obviously correct if terminates. Because if by induction, if all these calls here satisfy our requirement, satisfy these conditions, then the entire procedure also satisfies these conditions because it fixes. A resample even is not important for this conditional correctness. So because we fix all the clauses, including our C. But the question is why it terminates. So we need to show that it terminates fast with high probability, actually. So it will terminate with probability 1, but we don't want to go into infinite things. So we just prove that it terminates fast with high probability. So this is here we need some complexity argument. Okay, let me stop here and see whether you understand, whether I explain correctly and clearly what is the algorithm. So the algorithm, actually, what is different from the algorithm explained by Mario before? Here we have some very specific, what Mario said. Just we take some bad clause and correct it. And then take another bad clause and correct it, and so on. And here we have some specific order of doing things. So if we started with fixing some clause, then C. Then we make a resample, and then what we do, we do apply these things, the same procedure, to the neighbors of C only. And then for each of them, we make, maybe including C itself, for each of them, we also made some calls, recursive calls of the same procedure. So we go into call our procedure for some other neighbors. And for some of them, maybe no other calls are needed if everything is satisfied. For other, we need to call something and so on. So instead of our general, and our algorithm just looks at this tree in this order. We call this, then it creates a call here, then it creates a call here, then we somehow return here, but we don't make a call. We go here, then we go here. So we just go along in this order. We make calls for every vertex. So the difference with what we have before, just the resampling plus some special tree order of these resamples. Okay, so what it would be nice to for all of us to understand in the same way is what is our problem, what is our conditions. We have K, C, and F. We have that many neighbors. And what is this specific algorithm, how we fix the clauses in some special order by recursively calling this thing. So this fix is called, create several recursive calls here.
Am I correct to understand that we can have a situation with fixed C, it calls its neighbor,
Yeah.
C prime, and in fact when we resample C, it is again false, and then C prime calls C back.
Yeah,
C
it
back
can.
calls C prime, and we can in principle has some.
Yeah, so there are several possibilities. For example, what you say, we made a resampling for C, and then it makes some C prime false. Yeah. We make a resampling for C prime, and then it makes C false. Yeah. And then C is somewhere here. At some moment, we look at C, and it again makes some resampling, and after that, maybe we again see C prime or whatever. So there are quite possible that we return to the same vertex many times along the path, many times in different branches. It's always possible.
So actually this graph is not a tree. If we consider
No, it's a tree of calls. What I'm drawing, it's not a graph, not our graph of dependence. It's just a tree representation of recursive calls. So the same vertex appears many times. Also, there is possible that we, for example, we make a resampling and still C is false. And again, we make another resampling and again C is false. So we get just something like this. And this is also possible. So C can appear in different places. What cannot happen, C cannot appear in the same two neighbors, because after this call, whatever it is here, after we make this call, C is true. So we never return to each of the recursive call by our assumption doesn't destroy anything which was after it goes out. Doesn't after the return, it doesn't destroy whatever was true. So on this level, we cannot have C again, but still we can have C somewhere in the other recursive subtrees. Okay, so this is this algorithm. So is it clear? Are there some questions? So just please raise your hands who understand this, the problem in the algorithm. Okay, okay. So now let's say what is, we will repeat the argument of Mario, of Mozart. So what is a log here? And here we have a more simple, we don't have this special kind of trees and we don't witnesses trees, it's more simple. So, but the log again is the sequence of resampled clauses in the order of algorithm. I don't know how to say algorithm execution. I don't know. And there is also main lemma that the log plus final values of variables determine all the process, and in particular all the random bits used during the process.
And final values here are not the values after the process terminates. One values.
Okay, so it's true if the process terminates, but also it's true if we stop it artificially at some moment. Imagine we just at some moment decided to stop, and then there are some final values of variables, and then there is a log up to this moment, which clauses were resampled. And what I'm saying, that knowing all this information, we can find out what are the coin tosses. So actually, during our algorithm, we sometimes toss a coin. And knowing all these coin tosses results can be now reconstructed completely. And actually, this is trivial. So we know that the sampling was for clause 1, clause 2, clause 3, and clause n. And we know all the variables after the end of this. After this step, maybe we just artificially stopped here. Maybe if we so on this tree we maybe did not come to the origin. We just looked at some moment. So we know that this is the variables after all the resamplings. And so, for example, we know what are the variables in the clause Cn, because they are just in the final variables. So we know the variables in Cn after this step. But also, we know Cn variables before the step. Why? Because there is only one reason to make a resample. A resample is made when the clause is false. So, and each clause is a disjunction of some literals. So it prohibits exactly one, is false only for one values. So we know that because they made Cn false. And then, so we know all the variables at that moment. And then we know which variables were used for Cn minus 1 because they are in this list. And also we know all the variables before this last moment because here Cn minus 1 false. And this we can continue and then reconstruct everything. Actually, we can reconstruct even initial variables, and also we can reconstruct all the random bits used during the process. Okay, but so this is lemma, and maybe I should say before why we are interested in this. Because we will show that if the protocol is long, this n is not good because n is the number of something. Okay, let's be m here. If the protocol is long, it allows us to describe random variables shorter than it's possible. So the log becomes simpler than just the list of random variables. This is the contradiction. So this is the plan. And we are actually very close to the end of this argument, but just it's important to there is, if everything is trivial here, actually, if it's not clear, that's my fault, because there is nothing, no non-trivial steps were made up to now, and they will not be made later. So, okay, yeah.
Question in order to clarify this. Up to that moment, we haven't used this difference between our algorithm and algorithm that are.
Yeah, we haven't used a lot of things. First, we haven't used this difference. Second, we have some assumption, which is crucial assumption, which says that we have this one, that we have a bounded number of variables, bounded number of neighbors. And now it's just, you will see how we use this. Okay, any other questions? So who thinks that it's clear what is happening? Let's try.
What happens when we can get the situation when one clause is satisfied and all its neighbors are satisfied, but the whole formula is not satisfied? Then we should choose another clause.
No, there is a general algorithm which consists of calling fix for every false clause. So in this algorithm, we try false clauses one by one. Actually, it's not real for algorithm, because we don't make the list of. Okay, we can also do this, but we apply. We look clause by clause, and if they are bad, then we fix them. And but what you are saying is true. If we look at the clause which is true, we don't do any fixation is not used at all. So only false clause needs to be fixed. Okay, so any question, or it's not so unclear that there is you even cannot ask something specific. Okay, let me finish argument. It's very, very close to the end, and then maybe we'll go again and see what is happening. So now, how can we describe our log in a simple way? Maybe some of you already got this idea. How do you do this? So we have a tree, and this log is just the sequence of the vertices in the order of this tree traversal. So it's enough to specify just this tree. So tree determines log. When I specify tree, means that we specify also the order of vertices. So it's not just what are the suns, but the order of suns. And so how we specify the tree? There are some steps when we go up in the tree. And then we need k minus 3 bits to select neighbor. We assume that we have at most 2 to the k minus 3 neighbors. 2 2 to the k minus 3 neighbors.
Including the clause itself.
No, if we just if we just say at some step go up, we need to say at which all the neighbors are somehow ordered, including the clause itself. Yeah, including the clause itself. So it's not an optimal bound. Even more, it should be 2 to the k divided by e in the good lowest local lemma. So we have a weaker thing. We have 8 here. So this one is not a. I don't know how to say it in English, but снявши голову по волосам не плачут. This is much more weaker bound that so we already gave up a lot. Okay, so we need k minus 3 bits to select neighbors, and we should also some bit which says that we go up, not down. And if we go down, we need only 1 bit. We should say this just that we go down. So for each edge, up edge, we need k minus 2 bits, and for each down edge, we need 1 bit. And of course, the number of down edges is less than the number of up edges because we never go below our original thing. So we need at most k minus 2 bits. K minus 1 bit, sorry, because k minus 3 plus 1 here and plus 1 here bits per up steps. And at each up step, which is mean per 1 resamplings. And this is instead of k bits, random bits used for resampling. So what we see is just this wow, what an interesting thing. Okay, so let's so we have k minus 1 bits. So here is the main thing. So here is where is our contradiction. So now we can describe the tree using k minus 1 bit per vertex. And and knowing the tree, we can reconstruct all the bits. Also, we need the final bits, but they do depend on the length of the tree. So length of the sequence. So they are small if the sequence is long. So if the sequence is long, then the advantage which is obtained during this economy of 1 bit per vertex is bigger than the additional information needed to proceed the final values of the variables. And so contradiction for long resampling processes. Okay, this is the end of the argument, and okay, so who thinks that the argument is clear? Okay, but maybe you can ask something. Yeah.
Where does the proof is not correct for short process, resampling process?
So say it again.
Where do the proof does not hold for short resampling process?
For arbitrary resampling.
For small ones. You have a contradiction for a long resampling process, right?
He's asking why do we need to consider arbitrarily long processes?
Oh, why we? Oh, yes. Sorry. For short sampling, yeah. The problem is first of all this counting is really asymptotical. When we say if we want to use Kolmogorov complexity, this is always asymptotical. But there is more important thing. Even if we use normal counting, the problem is that we have some final values of variables. So we need final values plus k minus 1 times the number of steps is the total number of bits to describe everything. And we get a contradiction if it's smaller than k times the number of steps. So this means that k should be larger than the number of final values. Also, actually, if we are serious, we want to have some bound, probability bound. So we need to know that with high probability, the process is short. And if we just have this contradiction, this means that for some random values, it will be impossible. So to have the big probability, small probability of error, we need this discrepancy to be large, because it's actually 2 to the minus this discrepancy, which is the probability of error if we seriously count things.
But still the number of fixes should be proportional to n? What's that?
Still the number of...
So how many times do you need to fix?
No, and in this way we get a weaker bound, I think, because we do it separately for each fix, and then actually we can analyze the entire thing, because if we finish with one clause and continue with other clause, still the reconstruction of random bits is possible. But the only thing, actually, there are these recursive calls of fix, and there is a basic cycle at the beginning. So the basic cycle is a kind of exception, because here we have an arbitrary number of clauses. So arbitrary number of sons of the root. So if we want to make a better bound here, we need to go into this counting. But still you can do something. I don't know. I didn't check whether it gives comparably good bound. Yeah.
I'm not sure whether I understand. Do we assume that this process is finite?
No.
Why?
What I'm saying, that I say that if let's agree that we stop this process after some number of steps, and I'll say that the probability, if this number of steps is big, then the probability that it indeed will that long is small. Because if this is indeed that long, we have this kind of inequality, which means that the random bits used in our process have short description. And so this is possible only for very special, for a small fraction of all possible random bits. So the probability that we have if we have a long thing when this difference is, I don't know, d, the probability of the process will be that long is, 2 to the minus d, somehow. If we make a serious counting.
But it can happen that they just go in a loop or something.
Yeah, no, of course, there is a small positive probability. Just we can say in two ways. We can say that if we take a non-compressible bits, then we are guaranteed that it will stop at some bound, at some step. But what we say more specifically, that if it's long, then the bits are that compressible, and this means that this has small probability. This is a kind of relation between complexity and... Okay, so I see that it's not very clear still.
Can you just
Yeah.
repeat what you just algorithm with no proofs or explanation, because it's very hard to keep in mind.
Okay, so let's try to go again. So this is a statement. So it's okay, or we should. So it's at C and F. There is a closest size k, and there are just a bit less neighbors than the possible assignments for each clause. So it's a bit smaller than 2 to the k. And then it's enough to have a satisfying assignment. And the structure of the algorithm is that we look at all clauses one by one, and if it's false, we fix it close. And fix means we call some recursive procedure. And this recursive procedure is that we, very simple, we resample the clause itself here. And then for all the neighbors, we recursive, which are false, we recursively fix them. And the proof, the specification for the procedure, which can be proved by the induction on the as usual for recursive procedure, is that it makes our clause true and doesn't destroy any other clauses which were true. It can make actually some other false clause can make it true, but this is not a problem. So this is so the structure of the algorithm is like this. Oops. It's very interesting. There are some completely different. So how we go to the very no. Okay, maybe we should just move sequentially. Oops. Yeah, it's this way. So what I wanted to show, the structure of algorithm, is shown here, the general algorithm. This is the loop, main loop. And here we have the calls of fix, of C1, fix of C2, and so on. They are all the clauses. Sorry? Yeah. Yeah, we don't know whether it terminates or not. But we know that if it terminates, then it's okay. So we from now on, we analyze only one call of the procedure starting from some vertex. So we don't ignore now this main loop. So we just analyze one specific thing. And what we do, first, while watching how this procedure goes, what it calls, we write two things. First, we write a log. Log is just which clauses were resampled. And there is more detailed version of the log, which is a form of tree. And this tree says, just shows which call were caused by other call. So if we just, the relation is that if we look at this recursion call tree, and if we follow this tree in this order, in going along this, then we just get this our log. So the tree determines the log. And the log determines the random bits. So here we have mentioned that tree determines the log, and here we say that the log plus final values of variables determine all the random bits that used during the process. So is it clear why the tree determines the log? Yeah. Another, how the log plus final values determine the random bits. This is because we can go backwards. We know the final bits, and we know that if something is called, is resampled, then it's just because it was false. So we know how it was before. And now we know, just make one step before, we know all the bits now, and if something was resampled, we know which bits were used as random bits, and we know why it was that was what before. So we can reconstruct all the random bits going in that order. So then we see that the tree determines the random bits. And if our computer, this is true for any initial segment of our log and our tree. So we stop. We do not assume that the procedure terminates. We just make some number of steps, and after this number of steps, we have the tree, we have a log, and we have random variables, and the tree determines the log, and log determines random variables. And now the contradiction, or the last step, is that this is possible only if random bits are compressible, because the tree can be described by fewer random bits than the actual number of random bits used for resampling. And this is explanation, here what the explanation why. So how do we describe the tree? We just follow how we go up and down. And if we go up, we need to say at which neighbor we go up. And this requires k minus 3 bits. And also we need to say that we are going up. And if we are going down, we need to say that we are going down. So we need k minus 2 bits for up and 1 bit for down. And also we can count them together because the number of down steps is not more than the number of up steps. So actually we get k minus 3 plus 1 plus 1. In total we get k minus 1 bit per vertex, per resampling. So it's smaller. Here was this comparison. It's smaller than k bits. So if there is a also there is some additional thing. We need final values. But if the number of steps is long, then this is a main term, and this becomes much less than this. And so the probability that indeed random bits used for the sampling are compressible, the probability is small. So the probability the process is long is small. So of course we can say how long it, how small it is, and so on. But this is a kind of a computation which I'm afraid I cannot really. Okay, so yeah.
Can we improve the encoding of the tree? So what
How?
do we need?
Let's
We
see.
need these up and down bits. So
But how you encode the tree then?
just to enumerating the child of the current node.
No, every child has its ordinal number in the list of neighbors. That's true. But how do we imagine we have this tree? So what do we specify?
So I need some kind of delimiter which. So I don't have the answer. So I'm asking a question. Can we improve the amount of information to encode the tree? So to have the in the statement of the theorem, not the 2 to the power k minus 3 constant, but
Yeah.
2 to the power k minus 2. Or this is the. So I see that this is enough for your.
Yeah. But can we do something better and come closer to divide it? But it's not obvious, at least, because we need something with some estimate in terms of the number of visited vertices. Of course, for example, we can imagine we try to just describe which sons, which neighbors were used as sons. Then it's enough to use only 1 bit per neighbor. But if they have many neighbors and we use only one of them, then it's not an economy but a loss. So here we use, in this thing, we use k minus 1 bits per vertex. But if we just want to specify, for example, just a list of all used and unused neighbors, it's enough. But then it's long even for one. No, maybe we can count it more seriously. We can count the number of subsets of a set and.
Write down the size of the subset. It's still.
Yeah. So what we need to encode, we need to encode the subsets of different size in such a way that the length of encoding is proportional to the size of the subset with some coefficient which is smaller than k minus 1 or something like this.
If just half of the children are in the subset, then
No, half of the children is good because then we used just so we use 1 bit for each neighbor. So if half of the neighbors are used, this is actually 2 bits per vertex. It's very good, but it's not guaranteed. Yeah. Okay. So are there any questions or? Yeah. So who thinks that it's now clear? Are there? not good. Not good. Okay, but I am afraid I really, maybe if you have some questions, there is a chance, but it's too late. Okay, so we have now student talk, so Shannon theorem probably should be skipped. But it's finally I can say that it's in the book. And so I still have one copy, so if somebody really promise that he will or she will read the book, then I think there will be no more than one person with this very important promise. So you can take the book, and anyway there is a file available in the internet.
I'm going to check it later.
Sorry?
I'm going to check it later. Whether this person read the book.
Yeah, probably yes. Yeah. Probably yes, yeah. Okay, so thank you again for patience. I'm sorry that it was not, probably it can be explained better, but doing this in English and it's some additional difficulties, so maybe I can explain answer questions in Russian. And okay, thanks.